very, very unorthodox solution. And then eventually on the Sunday morning, when the previous orbit, the 1 o'clock time, passed, we saw that the spacecraft had survived. So it had managed to fly over the rim of this crater thanks to the very small change in the altitude that we have managed to implement. And then the happy end was that at exactly the predicted time, the spacecraft hit the hill that was predicted originally, 7 o'clock in the morning on Sunday, 3rd of September 2006, with everybody present, and success eventually was achieved. So this is an example of how, on one side, thinking out of the box, and on the other side, flexibility of the spacecraft allows solving a problem which apparently is not solvable. One day, one of the 4 cluster spacecraft coming out of an eclipse, cluster went through periodically an eclipse phase, so coming out of the shadow of the Earth, at the first contact did not transmit any telemetry. So we basically, our team was sitting in the control room and not receiving any information from the spacecraft. The station was still receiving a radio frequency carrier. So the signal was there. We knew that the spacecraft was there, and we knew that it was transmitting. But for some reason, only the carrier. There was no modulation, no telemetry. So our team and our control systems were completely blind. The team did some investigation first, tried to command in the blind the spacecraft. It was clear that when cluster was coming out of the eclipse, and it was sort of switching on gradually all the units, the switch-on sequence of the units obviously had not worked properly in this state. So this was clear, but we didn't know what this state was. There was no information. So the team sat there and decided, well, we have only one source of information, which is the radio signal. Is there a way we can do some tests by commanding and try to modify this radio signal, the shape of the radio signal, to see whether commands are received and to see whether we can get out of this situation? So that's exactly what they did. They selected commands that could modify the shape of the radio signal. For example, the height of the radio signal, by switching on and off the ranging transponder, you could see that this height would change. And so we sent these commands, and in fact, we noticed that the shape, the height of the radio frequency carrier was changing. This was very important. It showed that the spacecraft was able to receive commands. This was, of course, not enough, but already a very good step forward. Then they went on with this by sending commands that would activate or switch on the onboard computer, and they saw that those were not received. So relatively soon, they could discriminate and they could say, good, the spacecraft is receiving a certain type of commands and executing them, what we would call hardware commands, but it's not decoding software commands. So we knew the problem was not a hardware problem. It must have been something in the onboard computer that was not able to decode the software commands. The team went on with this investigation, and by trying possible sequences of commands, it focused more and more onto the status of some relays inside the onboard computer. Relays that we normally wouldn't change before the eclipse, but that possibly would have been put in a wrong position by this slow ramp up of the voltage at the exit of the eclipse. And in fact, by looking at the design and by trying various potential configurations, at the end they came to switch the right one, so to set up the proper configuration in the onboard computer, fortunately by hardware commands, so they were received. And about 48 hours after the moment that the problem occurred, by working practically uninterruptedly in the control room, the cluster team managed to reacquire telemetry. This was, of course, a big relief, an incredible success. And once they had understood what the problem was, they could very easily design a procedure that, in case this problem would reoccur, would reset the configuration of all the relays to the right situation. In fact, it happened many more times in the cluster mission, because all the spacecraft were periodically going through this eclipse and they were exposed to this potential problem. The story here is, again, thinking out of the box. Look at the tools that you have and try to get the best out of it. We're normally used to, our tools is thousands of parameters in the telemetry. At that time, the team had none of them. All it had was the radio signal. But they said, okay, how can we use this tool, the radio signal? How can we get information out of it? They managed, with the incredibly small amount of information, they managed to get out of the dangerous situation. EXOSAT was a satellite built in the 80s, and at that time, the majority of satellites were built still with hardwired logic. So basically integrated circuits that would have all their functions hardwired. There was no way to reprogram them. But EXOSAT was the first ESA spacecraft which actually carried on board a reprogrammable onboard computer. It was not there to drive the spacecraft. So all the logic of the spacecraft, of the platform, was implemented in hardware. This onboard computer was purely designed to do an onboard processing of the scientific data, to reduce them, compact them, elaborate them so that they could be transmitted in a more efficient way to ground. So only purpose was scientific. We had a dedicated person, a lady in the team who was specialist of this computer, could reprogram it, and she was trained to adapt the programs to the processing of science. One day the logic of the attitude control subsystem, the failure detection logic of the AOCS, basically failed. And the AOCS was detecting gyroscope failures even if there were no gyroscope failures. And since this was a hardwired logic, there was no way to change that. So every time there was a spurious detection, the spacecraft would trigger a safe mode, consume fuel, was interrupt the scientific observation. It was really a disaster. It was getting the mission basically to the end. So the team here thought, well, why don't we use the science computer to implement a very small routine, a more intelligent routine that will prevent the spurious triggering of gyroscope failures. So this routine was implemented by this lady very, very rapidly in very basic assembler code at that time, where basically the routine would check itself the gyroscope health, and if the gyroscope was actually healthy, it would keep the hardwired logic of the AOCS disabled. But if it would detect that there was a gyro problem, it would enable the hardware logic, and then the AOCS would trigger the switchover of the gyro in the safe mode. Since we implemented this, no more spurious failures occurred, and the spacecraft continued, the mission continued. So it was a way to save a problem in the hardwired logic of the spacecraft with the only flexible part of the spacecraft that was there, a reprogrammable onboard computer. Nowadays, all spacecraft have reprogrammable computers. We don't have this problem anymore. But that was the start of this new technology utilization. My name is Paolo Ferri. Welcome to my masterclass. Communications is fundamental in our job. It's communication on all levels, from the real-time communications in critical mission phases in the control room to passing information across team members, especially for long-duration projects where team members change roles, disappear, get replaced. So this is absolutely important for missions that last a long time. And finally, also across missions. Across missions, relevant information can be passed, has to be passed, and it has to attract our attention how we implement this communication flow across all parts of a project. Exosat was an X-ray telescope, so it was an observatory, and it was run like an observatory. There were a list of planned observations. The mission planners would put them in the right order, and then each scientist would get on a shift pattern an orbit to plan. An orbit was 4 days with a number of observations. Depending on the duration, there could be half a dozen till a bit more observations. The output of the planning was documented in a procedural book. It was basically a list of observations with the time, with the characteristics. And one important point in this planning was that each observation, in case it couldn't be missed because it had to be done at a specific time, or because there was a simultaneous observation from another telescope, those observations that couldn't be missed had an asterisk in this list, in this official output of the mission planning. So we knew that in case, in real time, we had the necessity of changing the plan due to what we still call a target of opportunity. Something that happens, a phone call from an observatory, and a scientist coming in with an idea that asks you to change the plan. For example, skip an observation. Targets of opportunity for an astronomy mission can be of two types. They are, in general, unexpected events, astronomical events. They can be on your source, the one that you're pointing at. Suddenly you see an effect that you want to follow for a longer time. So you want to extend the duration of your observation. Or they can be actually observed by other observatories on a completely different target, different source. And they communicate to you and they ask you, oh, can we do observations in parallel? Because I've seen, for example, a supernova, or I've seen a very unusual behavior of a specific source, and I want an observation also from you. We knew through this asterisk that some observations could not be skipped. So in case of a target of opportunity, we would have to execute it at a different time. The planner, just for convenience, would not only produce this official output in a book, but it would also produce a flip chart with a summary of all the observations. This was very useful because you didn't have to go through the book and find this list of activities. You had it on the flip chart, so it was a convenience thing. But this was duplicating the information which was in the book. On the flip chart, of course, the observations which couldn't be skipped, couldn't be cancelled, were also marked by an asterisk. And one day, I happened to be on shift. We received the request for a target of opportunity, and I looked at the flip chart. I saw that the upcoming observation did not have any asterisk, so it was fine to cancel it. And we implemented the target of opportunity. We canceled that observation. The next day, the planner came in and he saw what happened on that night, and was desperate because, in fact, we had skipped one of those forbidden observations, those which were marked with an asterisk. The problem was that they were marked with an asterisk in the book, but not in the flip chart. And on that night, I had looked at the flip chart and not at the book. So the confusion was created by duplicating the information And of course, when you duplicate information, the chances that you make a mistake and you create inconsistent information is very high. So it is essential in our work when we